Hello and welcome back to the class. Today we will look at chapter 6, which is earthquakes. And in this chapter we will learn about the mechanism of earthquake, how it happens, where it is more likely to happen, and what are the physics and geological processes responsible for this event. I have posted some videos on your Canvas page for this chapter. That will serve as a primer, provides you enough introduction about earthquake, how history of earthquake, where it has happened, and the effect of earthquake. So I would not discuss much about the definition of earthquake, how and where it happens, the history of earthquake. Those are very well discussed and described in that video. So please go through that, watch that video. Available in your Canvas page, and here in this video I will mostly talk about the geological processes responsible for earthquake. So let's dive right into it. What is the mechanism that generates large earthquakes? So first we have to understand what causes earthquakes. So for that you will need some understanding about plate tectonics that we learned earlier, that how we have these multiple geological plates and all of these plates are constantly moving, and when they are moving it is very likely that they will collide against each other. And there are three types of plate boundaries that we learned about: divergent plate boundary, convergent plate boundary, and transformed plate boundary. So in this chapter we will look at how all of these three boundaries, plate tectonic boundaries, are responsible for the formation of this process called earthquake. The definition of earthquake is the sudden movement of one block of rock slipping past another along a fault line. So this is how we define earthquake, which means there is a sudden movement of one block of rock slipping past another along a fault line. So I will just quickly define what is a fault. Okay, so I will quickly define what is a fault line. Okay, so here, so suppose this is your one plate, and suppose you have another plate here like this. Okay, and you have this fracture line here, right? So there is some fracture here, and as soon as these plates start moving along this line of fracture, then we will call it a fault line, right? So first it is a fracture when there is no movement along this fracture line, but the same fracture will now be called as a fault line as soon as the plates start moving past each other. And you can, if you look at the interface between these two plates, this surface is not smooth, it's very rough surface, right? But at this scale it looks like it is smooth, but if you zoom in, so it is not, it is really not smooth, it's very rough. There is a jagged face on this on the face of these two giant mass of rock or plates, and this is what causes friction, right? At the face of this these two plates there is a friction due to roughness of the surface, and that friction does not allow this plate to slide against each other. So what happens due to this this friction, since the plate cannot slide against each other, now the energy starts to build, right? And that energy will continue to store it at this interface, and as the time passes, more and more energy is built here, and a time will come when this excess of energy will be able to overcome the friction. So this friction is greater than energy stored, right? And when this friction become lower than or smaller than energy, that will lead to earthquake event, right? Because now these two plates have been trying to slide past each other to release this excess of energy, but due to friction they could not slide past each other. But now as soon as the energy can overcome this friction, this slide will happen, and depending on how long they have been prevented from sliding, that will control the energy released during this earthquake event. So that is a fundamental about earthquake, that it occurs around this transform plate boundary, where the two plates are trying to slide against each other, but they could not slide due to friction, and longer it takes for them to release this energy, stronger the earthquake will be whenever that energy will be released. So this is what it says here. Most faults are located on a sudden slip. Seismic waves radiate out from the focus hypocenter where slip begins, and Earth's surface directly above the hypocenter is the epicenter. So there are two new terms coming up, actually three: seismic waves, hypocenter, and epicenter. Right. So let's look at those terms. So seismic waves are the energy waves that are released during this when the slip will occur. As I said earlier, this energy will be stored due to non-slip, as the friction does not allow the plate to slip. The elastic energy will be stored, and that will be released in the form of seismic waves whenever the slip will occur. So this is again the same schematic about two rock masses, and this is your fracture or fault line where the slip will occur. So right where the slip will initiate in the body of the earth, that will be called as hypocenter. It is the interior body of the earth, and right above, if you project this point on the surface of the earth, that point will now be called as epicenter. So there is a difference. Hypocenter is the origin of slip in the interior of the body of earth. Epicenter is that projected point on the surface of the earth where the slip has occurred inside the body of earth. Okay. Weak earthquakes can be generated by volcanoes, landslides, and meteorite impact. So volcano, it's another geological event. We will look more in detail about it in the next chapter. So that also causes some shaking of the surrounding rock masses. So that can also destabilize these fracture planes, and that can lead to some further movement of earth mass. A landslide, which is mass wasting, we learned in the last class that how that can also sometimes be very stronger depending on how big of a rock mass is sliding. That can also cause some shaking, and that can also trigger some weak earthquake. Meteorite impact is another, when these objects or rock masses which are flying in the space, and they can hit the planets, and that can cause some of these earthquakes depending on how big that meteorite is. Destructive earthquake occur because tectonic motion builds up stress. So this is what I mentioned earlier, that as these plates are trying to slip past each other, and the friction does not allow them to slide, and that will lead to building up of stress, and that stress, longer it takes for the slip to occur, more stress will be built, and stronger the earthquake will be whenever the slip will actually happen. Friction keeps the fault from slipping. So fault is that line or the interface where the transform plate boundary is, where the two plates are trying to slide against each other. Slip initiates when stress overcomes friction. Elastic rebound, this is another term. So since rock masses, they looks very strong and cohesive, but in reality, if you look at them in the geological scale, with geological properties in mind, it will seem that they also act like a spring material. So you can squeeze them in, and as soon as the stress is released, they can recover their original undeformed position. So that is called as elastic rebound. So you can think of it this also in the case of earthquake, where the two plates are squeezed together, and due to the overburden mass, they cannot recover their original shape. So as soon as that weight is lifted, they will just suddenly release this overburden stress, and that can also lead to the earthquake events. So elastic rebound, that process where the rock after a long time of overburden pressure recover its original undeformed position. This is another example where you can explain earthquake event. So this is again, you have two rock masses or two plates. This is like your transformed plate boundary, and the analogy here is made with using a limber stick, just like a stick of any plant, and in the original state, that stick is not under stress. You are just holding the stick, but as you start to bend the stick, the stress will start to build, because now you are changing the original stable shape of this stick, and as you continue to bend it, a time will come when this stick can no longer sustain this external stress, and it will just snap or breaks. And that is exactly what happens in the case of this transformed plate boundary. So these two plates are trying to slide against each other, but the friction does not allow them to slide. So the stress will start to build, and the stress will start to build, and as the stress continue to grow, a time will come when the stress can finally overcome the frictional force, and when that moment will come, the slip will happen, and the earthquake or the seismic, a large volume of seismic waves will be generated, and that seismic wave will spread in the surrounding area, and that will cause the motion of earth or rock masses, which will called as earthquake event. Transform faults have many branches and fractures. So this transform fault, as you see here, it has multiple small branches which are spreading or originating from the main transform faults, and there are minor earthquakes that will happen around those smaller branches of fault lines. Offset occurs in distinct segments. Some segments display slowly with little shaking during fault creep. So fault creep is that slight movement of earth or the plates. So these plates are trying to move, trying to slide against each other, and when they can slide a little bit, not significantly, then it is called as fault creep. So this is a very small displacement of plate along the fault line, and that is called as fault creep, and it is discrete in nature. It does not continue for a long time. It happens and then it stops, and then the stress will build again, and then after a few years that will happen again. So those will leads to this sudden release of energy. So that will make your fault line safer over the time with this fault creep, because these fault creeps allow this energy to be released at certain interval, so that not a large volume of energy is stored or built here. So that will keep a big earthquake event from happening. So this is a good thing where the fault creep is, and if the energy can release at certain interval, so that whenever the big earthquake will happen, it will not be as destructive, because not so much energy has been stored on that fault plane. earthquakes occur in repetitive cycles because you can think about this sliding of the plate. As I said, the face of this plate is not very smooth, so the sliding will occur, energy will be released, the friction will again lock those plates in one place, and again they will try to slip more, so that another slip will happen, another release of seismic waves, another event of earthquake. So this is how it is a kind of a repetitive until it comes to a stable position where the friction can lock these plates again in a stable form. Rupture propagates in a discrete time period. So discrete time period, it means that it will happen, suppose now at 11 o'clock, and then another event will happen maybe at 1 in the afternoon, another will happen at 6 in the evening. So this is what it means, the discrete time period. So it is not continuous, this event of earthquake, but as these plates are trying to slide past each other and the friction is trying to prevent it, so this will continue to happen until the friction locks these two plates again in a stable position. This is one example in Southern California. So in early 20th century, in 1906, there was a major earthquake event in San Francisco. Here you can see this is a fence around some residential neighborhood. This fence itself has moved 2.5 meters. So this indicates that part of this fence was on one side of the transform plate, another part of the fence was on the other transform plate, and this transform plate has moved. So that's why there is this offset between the fences, or the part of the fences. So this offset is about 2.5 meters, which is about 8.5 feet. So that's quite significant movement, and this has led to a major earthquake event. Lots of life and property was lost and damaged and during this event. And right below this, in the south of San Francisco, you have the San Andreas Fault, and this San Andreas Fault has not seen any earthquake event in last 300 years. So it means that this plate, this is a transform plate, so no doubt that these transform plates are trying to slide against each other, but due to friction they cannot slide. So the energy has been building up, and it has been 300 years since a major earthquake event has occurred. So it means a lot of energy has built around this area. So the next earthquake event will be extremely devastating or destructive in nature, because it is believed that a lot of energy has been built which has not been released even by means of creep fault. There is not even a smaller earthquake event that has occurred in this area. So it is expected that the next earthquake event will be highly destructive in nature. Convergent plate boundaries, they generate compressional forces, and it can lead to mountain building and faulting associated with large earthquakes. Subducting plates form a megathrust fault, produce the most powerful earthquakes. Vertical motion underneath the ocean generates tsunamis. So when the earthquake event happens in the ocean, then it will lead to the event of tsunamis, because we have these tectonic plate boundaries submerged in the ocean, and there are convergent plate boundaries as well, which are buried in the depth of ocean. And if there is any transform plate boundary, and if there is any motion that will happen in the ocean, that motion or the sliding of the plate can lead to earthquake event in the ocean, and that will eventually lead to the tsunami. So there is another this example, mountain building. So that is here you can think about this example that I have given here. This is about the transform plate boundary. So the another one is where you can have two plates, they are not moving past each other, but they are moving towards each other. So that is one case of convergent plate boundaries. And the example here is given is mountain building. So then when these two plates are both continental plates, so in that case there will be no subduction, right? Because they have about the same density. One is not significantly denser, so they are both continental, and that will lead to the formation of this mountain structure here, right? And in one example here is Himalayan mountain in Indian region, right? I think the schematic is also given. So that is one example, mountain building, when two continental plates collide with each other, and that collision will also lead to production of large amount of energy, and that energy will be released in the form of seismic waves, and that will kind of transform into earthquake event. Are there any local faults? Not where we live in Florida. We are in the very passive plate boundary region, so there is not any significant earthquake event here. So what is the mechanism that generates large earthquakes? So make sure that you know this and remember this. This will be in your test. Stress from movement of tectonic plates accumulates in a block of crust until it overcomes frictional resistance and slips occur. So you can write this in your own words. If it seems very complicated, you can just write when the two plates at transformed plate boundaries are trying to slide against each other, the stress will build because friction does not allow them to slide past each other. And as more and more energy is built, this energy will eventually overcome the friction and the slide will happen, which will lead to the event of earthquake. Seismic waves propagate out from the hypocenter. So we saw earlier that hypocenter is the location in the interior of the earth where the slip originates, and epicenter is the projected location on the surface of the earth. Different types of seismic waves. So we will see that energy that we were talking about, which is released during the earthquake, those energy are released in the form of seismic waves. And so seismic waves that are traveling on the interior or on the surface of the earth due to these geological events are called as seismic waves. And there is a study of earthquake waves or seismic wave which is called as seismology, and then there is an instrument which measures the intensity and the strength of these seismic waves, and those instruments are called as seismometers. I have posted a video of this instrument as well, so that has a very clear description and animation that how it works. So I would not go much in detail. I will just quickly show this schematic and tell you this seismometer is located buried deep into the ground, and as the movement in this earth happens, there is this pen which writes on the paper. Depending on how this earth is moving, how fast it is moving, those motion will be registered here on this piece of paper. And later we can see, look at the amplitude and duration of this shaking of the earth, and that can help you determine how strong the earthquake event was. So please look at that video that I posted on Canvas about seismometers. There are two types of seismic waves. One is surface waves that the name indicates it travels on the surface, near the surface of the earth. Another one is body waves, just like the name indicates, it travels through earth's interior, and both are two different types. So we will see the classification. First let's see this schematic here. So here you can see the surface waves. It is running right around, hugging around the surface of the earth, and this is the interior of the earth. You can see core, mantle, and the top layer is called crust. You have these body waves called P waves and S waves. Okay, so you have two different types of body waves. So you can see they are propagating in the interior or in the volume of the earth, but the surface waves, it stays near the surface of the earth. And you have these seismographs or seismometers instrument that I just talked about. Those are located in different part of the earth, and they will register as these waves arrive at these different seismographs. So here you can see surface waves are traveling, body waves are traveling, and they are being registered at these different seismographs as they come across these different seismographs. So you can see the P waves, S waves reached at seismograph 1. Surface waves have also reached here. Seismograph 2 has also registered surface waves, P waves, and S wave. And you can look at the nature of these three waves as they register on the seismograph. It's very different. You can see the S waves has very high amplitude. S waves have a kind of a medium range amplitude. P waves has relatively small amplitude. So this is how you will know that what kind of wave has arrived at what time, right? So the time is also registered here, and these amplitude of different waves are registered here. And over here at seismograph 3, only P waves have arrived. S wave and surface waves have not arrived. So this indicates that P waves is the fastest one. It has reached very quickly to this farther region, seismograph 3, which is really far from the epicenter. But S waves and surface waves had not yet arrived. See, you can see that S waves is almost there, and surface waves is still much farther from the seismograph. So this gives you an idea that what is the relative velocity difference between these different waves. And so P waves, it travels fastest. S waves is second, and the surface waves are the slowest or the third amongst these seismic waves. Here is a further explanation about the waves, primary waves or P waves. This again, the nature of the motion is different for these different waves. P waves, it just act like a spring. It goes compression and expansion. This is how it moves. So as it travels, this is what it causes. It compresses the rock mass, and then when it passes through it, the rock mass can expand itself. Like we talked about elastic rebound. So this is what happens when the P waves or primary wave is traveling through the rock. On the other hand, S waves has more like a wave-like motion. So if you are holding a rock and then if you just wave it in the vertical direction, it will just create this wave-like motion. So this is how the S wave travels. And the surface waves can also be classified in two different types based on their motion. So the first one is more a wave-like or rolling wave-like motion. You can see here the S wave, it has a surface waves. Surface waves can have two different types of motion. One is like a wave, another one is sidewise movement. Others move side to side, most damaging type of ground motion. So the surface waves are the one which are more destructive, and between the surface wave, the one that moves sideways, because it is going to damage the foundation of different structure and buildings. So you can see that as these waves causes the rocks to move sideways, and that will cause more destruction of engineering structure, buildings, houses, dams, and structures like that. On the other hand, wave with the surface wave, it moves like a wave. It does not cause significant damage to the foundation of any engineering structure. It may cause some depression in the ground, some sudden rise in the elevation, but it will not cause much damage to the foundation of the earth. So depending on what type of S wave has passed through your region, your neighborhood, you will see these different kind of geological change in the rocks. Speed of travel is very different for each type of wave. As I discussed earlier, P wave is the fastest, S wave is the second, and surface wave is the third. And another thing I want you to notice is the amplitude of these three different waves. Surface waves have the highest amplitude, S wave has the second, and the P wave has the smallest amplitude. So these are the factors that you can list when I ask you to tell me the difference between different body waves like P waves and S wave. I may ask you to write me two different types of body waves and tell me the difference between the two. Okay, so you can write about the amplitude and this and the speed at which they travel. Again, a review. What are the different types of seismic waves? Surface waves travel at the Earth's surface, and body waves travel through the interior. Body waves are two different types, P waves and S waves. P waves travel faster and it has a push and pull kind of motion. S waves move material from side to side. How are seismographs used to locate an earthquake epicenter? So this is described better here in this photograph. So you have these different seismographs located in different part of the earth. Depending on where the epicenter of the earthquake is, it will be registered at these different seismographs at different times. And by looking at their time of arrival at different seismographs, we can triangulate the location of the epicenter. So this is one example. The epicenter is here somewhere in the China, and it was registered in a seismograph in India, in Paris, Europe, and one in Australia. So depending on the time of arrival, we can triangulate where the epicenter is. Difference between P and S wave arrival time increase with difference from epicenter. Multiple seismographs are used to triangulate the epicenter. This is just about the scale in which the earthquake is measured. So I want you guys to just go over this in the textbook. Section 6.5, what destructive forces are triggered by earthquake vibration. So this is also talked a little bit about in the documentary that I uploaded on Canvas. So make sure you watch that documentary. It talks about all of these different events that is triggered by earthquake vibrations. One is ground motion. Obviously, the ground will move, the foundation will be damaged, and a destruction will happen due to the collapse of these different engineering structures. Liquefaction is another very interesting phenomenon that happens when the semi-saturated soil or saturated soil, it completely lost its strength due to the motion of the earth mass. So during the earthquake event, the earth mass will be shaken rapidly, and that will lead to this soil mass to lose its strength. So you have these large building structure, engineering structures like building, dams, houses are sitting on a foundation, and this foundation for lots of time it is made out of soil. And that soil will become like a liquid. In a normal condition, that soil has a very strong strength, and it is very cohesive, but during the earthquake event, that same soil mass is shaken so rapidly that it is now lost all its strength, and it is now acting like a liquid. So the foundation will give in, and that will lead to the complete collapse of these different engineering structures, and that will lead to even much larger destruction or loss of life and value. Landslide is another event due to the earthquake event. We saw earlier that earthquake is one of the trigger for mass wasting. So that is again depending on where it occurs. If it is around a residential neighborhood, or then it can cause even more damage to life and value. Ground subsidence is another one. When suppose one of the plate suddenly subside or settle in the ground, and that event is called as ground subsidence. Fires, that is kind of a secondary event, because now we have lots of these gas pipelines that are buried under the ground, and due to these earthquake events, these pipes can be damaged and the gas will be released, and that can cause some fire. Even you can think about the electric lines are also now buried under the ground, so these electric lines can short circuits, and then there's a sudden release of these gas from the damaged gas pipe, and that can cause some big fire in the residential neighborhood. So that is another effect. Fires is another effect of earthquake events. Tsunamis is another one. The earthquake event, when it happens in the ocean, that can lead to the formation. This sudden release of energy can cause these large waves to form. The waves will travel towards the shoreline and with so much energy, and that will cause a lot of destruction in the coastal areas. So these are the different destructive forces that are triggered by earthquake vibration. Make sure that you remember this, maybe in your test. What are the major earthquake belts? So now we will look into the region where the earthquakes are very common. So first one is Circum-Pacific Belt Convergent Boundary. You can see in this global map, so this is all the red ones are those earthquake prone region. First one is Circum-Pacific Belt. This is all convergent plate boundaries. So here the oceanic plate are in some cases converging against another oceanic plate, and in this case of North America, South America, these oceanic plates are converging against continental plates. So there is a subduction zone all around here, and which leads to a lot of earthquake, right? So over here in the San Andreas region, this is a transformed plate boundary. The plates are trying to slide against each other, and that can also lead to the earthquake event. Another major earthquake region is Alpine Himalayan belt. Here this Indian subcontinent, it used to be part of the African plate, but at some point it broke off and it started moving northwards toward this European plate, and after traveling, then it finally collided with European plate, and that led to the formation of this Himalayan mountain. We will see more in detail about this mountain building process in the next chapter, but here just to understand, this Indian plate is constantly moving up against the Eurasian plate, and that is what causing a continuous convergent boundary between these two continents. And as these two continents are colliding, there is this strong earthquake region which is forming here. Third one is Mid-Atlantic Ridge, which is right in the middle of Atlantic Ocean. This is a divergent plate boundary. And there are lots of transformed plate boundaries as well right along this Mid-Atlantic Ridge, because this is not a very smooth boundary. If you zoom into this boundary, you will see lots of transformed plate boundaries as well. So this divergent plate boundaries, as it is diverging, that can also lead to some shaking or movement in the plate, and that can cause some minor earthquake events. But the major earthquake events are due to this two different types of convergent plate boundaries. One which is around the Pacific Ocean, which is Circum-Pacific Belt. Another one is around this Indian Eurasian region, which is again another convergent plate boundary between these two continents. So these are the major earthquake belts around different plate boundaries. Here want you guys to definitely remember this. Where are the major earthquake belts? Remember all these three examples: Alpine Himalayan belt, oceanic ridge system, and subduction zones around the Pacific Ocean. Want you guys to just read through this. I have discussed this before, the layered structure of the earth. We talked about this in plate tectonics, crust, mantle, core, how there is a density stratification that leads to the denser material all submerged together in the core of the earth, iron and nickel being the dominant component in the earth core, and then lighter material rose toward the surface, made mantle and crust of the earth. And so this is the interior of the earth. I just want you guys to read through this, make sure you understand it. There are more videos available in the previous chapter in plate tectonics, so you can look through that too. Seismic waves are the only way to see inside the interior. So this is how we know the interior of the earth, because this question comes to mind, that how can we be so certain that there are 3 layers in the interior of the earth, crust, mantle, core. So seismic waves are the one that help us determine the thickness of each layer, the composition of each layer, because these waves travel differently as it travels through different regions, because the density of the material changes, the temperature of the material changes, and that changes the speed at which these waves can travel. And sometimes there are materials that does not even allow the waves to travel through them. So that is another indication about the density of the material. So if the waves cannot travel through them, then that is another sign that it is a very highly dense material. So the waves are simply just reflecting back from those materials. So this is again just a schematic here. The seismic waves, as they are traveling, sometimes they can reflect, sometimes they can refract, sometimes they can just pass through the material. So read through this, it's in your textbook. Why is earth layered? Physical and chemical segregation of molten material. So as I discussed earlier, that there is a buoyancy driven segregation of material, or density due to density difference. These materials accumulate at different depth of the earth. The lighter material will rise toward the surface, the denser material will make the core of the earth. How are seismic waves used to describe earth interior? Since the seismic waves travel differently through different material, due to the density of the material, they can go through reflection, refraction, diffraction, and the velocity at which they are traveling, that will be used to interpret the composition and temperature of rock through which they are traveling. What is each of Earth's layer like? You have these 3 distinct layers: crust, mantle, core. Crust is the outermost layer, mantle is in the middle, core is in the center of the Earth. It can be further subdivided into zones based on physical properties, solid or liquid, or strength. Here just some of the facts that I want you guys to remember or memorize. Rock crust is the thinnest among the 3. It can be divided into oceanic crust and continental crust. Oceanic crust is much denser than the continental crust. Oceanic crust is composed of basalt. It is 7 kilometers thick, whereas continental crust is relatively much thicker than the oceanic crust, but it is relatively lighter in density compared to the oceanic crust. So continental crust is mostly granitic in nature. It has lower density, whereas the oceanic crust is basaltic in nature, which has higher density. Oceanic crust is thinner compared to the continental crust. So make sure you not only remember the name, but also the difference between the two. A mantle, it's about 2900 kilometer. It is the thickest layer between these 3 layers, crust, mantle, and core. It is 82% of the earth volume. So the majority of the earth volume is in the mantle. Chemical change at boundary between crust and mantle. Uppermost mantle is peridotype. A stiff top of upper mantle is lithosphere. It is cool, rigid. It's about 100 kilometers thick. A weak portion below is asthenosphere. Upper asthenosphere is partially melted. Lithosphere moves independently of asthenosphere. So we saw all this detail in the previous chapter when we were looking at plate tectonics, that how you have these plates which are sitting on the mobile asthenosphere layer, which is gel-like material that allow the plates to move, and that's what leads to this whole theory of plate tectonics, how the plates are moving. Okay, so just review this again from previous chapter, or in this chapter also there are more details given in your textbook. Core is made out of mostly iron and nickel. It is the most dense, 10 gram per cubic centimeters. Outer core is liquid, inner core is solid sphere. And this is where the iron, the molten iron, which is creating this earth magnetic field. So since the earth is rotating and you have this molten iron in the center of the earth, that molten rotating iron which is creating the magnetic field around the planet Earth. So this is just a schematic of these three layers: inner core, outer core, mantle, and then you have crust on the top. Another review, what is each of Earth's layers like? Crust is thin, solid, oceanic, it is basaltic in nature. Continental, it is thicker, but it is you can just think of it as granite or granodiorite. Mantle is solid. Crust and upper mantle together, it is called as lithosphere. Since the crust is two different type, oceanic and continental, lithosphere is also two different type, continental lithosphere and oceanic lithosphere. So the difference between lithosphere and crust is lithosphere is this layer which is upper layer as well as crust. So lithosphere will definitely be thicker than the crust. Crust is just crust by itself.